In 1895, a physicist named Wilhelm Röntgen accidentally discovered that a beam of radiation could pass through human flesh and leave a shadow of bone on a photographic plate. He called it X-radiation because he did not know what it was. Within weeks, hospitals across Europe were using it. Within a year, it had changed medicine forever. This is what actually happens when an X-ray passes through your body. An X-ray is a photon, the same fundamental particle as visible light, the same particle that carries energy from the sun to your skin. The difference is energy. Visible light carries enough energy to stimulate the cells in your retina. X-ray photons carry roughly 10,000 times more energy than that, enough to pass through soft tissue, enough to be partially absorbed by bone, enough at high doses to ionize the atoms they encounter, breaking chemical bonds and damaging DNA. This is why X-rays are both useful and, at excessive doses, dangerous. But the key word is excessive. Inside an X-ray tube, electrons are accelerated across a voltage difference of between 40 and 150 kilovolts. They strike a tungsten target at high speed. Two things happen. First, the electrons decelerate rapidly, releasing their kinetic energy as photons. This is called Bremsstrahlung radiation, from the German braking radiation. Second, the electrons knock inner shell electrons out of tungsten atoms. When outer shell electrons fall inward to fill the gap, they release characteristic X-ray photons at specific energies defined by the quantum structure of tungsten. The result is a beam of X-ray photons with a spectrum of energies directed toward the patient. When an X-ray photon enters your body, one of three things happens. It passes straight through, it is absorbed completely, depositing its energy in the tissue, or it is scattered, deflected at an angle, losing some energy in the process. The probability of each outcome depends on the energy of the photon and the atomic number of the material it encounters. Bone contains calcium, atomic number 20. Soft tissue is mostly water, hydrogen and oxygen, atomic numbers 1 and 8. Higher atomic number materials absorb more photons. This is why bone appears bright on an X-ray image. More photons are absorbed by bone, fewer reach the detector. And that difference in transmission creates contrast. The image is a map of differential photon absorption. This is where most people have the wrong intuition. The radiation dose from a standard chest X-ray is approximately 0.1 millisieverts. For context, you receive approximately 2 to 3 millisieverts of natural background radiation every year, simply by existing on Earth. From cosmic rays, from naturally occurring radioactive materials in soil and building materials, from the potassium in your own body. A chest X-ray delivers less radiation than 10 hours on a long-haul flight at altitude. A CT scan delivers more, approximately 7 millisieverts for a chest CT, still comparable to 2 years of natural background radiation. Medical imaging is not zero risk, but the risk is small, well characterized, and almost always vastly outweighed by the diagnostic benefit. The medical physicist's job is to ensure that every scan delivers the minimum dose required to achieve the diagnostic objective. No more. A standard X-ray is a two-dimensional projection. All the structures along the beam path are superimposed onto a single plane. Depth information is lost. Computed tomography solves this. A CT scanner rotates an X-ray source and detector array around the patient, acquiring hundreds of projections at different angles. Each projection is a one-dimensional sample of the patient's attenuation profile at that angle. To reconstruct a cross-sectional image from these projections, the scanner applies a mathematical operation called the Radon transform, described by the Austrian mathematician Johann Radon in 1917. The inverse Radon transform takes the complete set of projections and calculates the three-dimensional distribution of attenuation coefficients within the patient. The result is a true three-dimensional image, with depth, with spatial resolution, with the ability to distinguish structures that would be impossible to separate in a plain X-ray. A piece of mathematics from 1917 running in real time inside every CT scanner on Earth. CT scanning detects disease that would otherwise be invisible. Early-stage lung cancer, pulmonary embolism, intracranial hemorrhage. Conditions that are fatal if missed. Conditions that are treatable if found early. The radiation dose is real, the benefit is also real, and understanding both requires physics. Not approximation, not intuition. Physics. Next on this channel, MRI. How a machine the size of a room uses a magnetic field 100,000 times stronger than Earth's to image the soft tissue of the brain without a single X-ray photon. The physics is extraordinary. See you there.